to deliver to the matters.
Good evening to all of you. Today's meeting is being arranged by the CHENNAI branch of the Indian Rubber Institute, along with Rubber and Plastic Department, Community Law University. For this meeting, we have with us Dr. Pradeep Martin, lecturer in Rubber Technology, and he will give you a talk on prospective perspective of a sustainable latex industry, technology, application, and opportunity for innovation. I would like to extend a warm welcome to you, Dr. Martin. I also welcome the delegates who are attending in person, and we are also having delegates online. Understand about 12 people have joined online. I welcome all of them. We have also important people in the industry. Mr. Isaac, head global R&D Apollo Tracks, he is with us now. That the rubber industry, the yardstick is growth based on rubber consumption. Now, in graphical representation, what is seen here, 50% is occupied by tire industry and last 20% is occupied by non-tire industry. In non-tire industry, you have different things, bicycle tires and tubes, footwear, and also belts and hoses, thread rubber and latex products, and then others. In the category others also has got a good volume of consumption, particularly in auto sector. Lot of rubber components are used both for car and trucks and even in scooter, motorcycles, etc. There's big concentration of these sort of automotive components in and around China. In the for students, both undergraduate and inter students, you have to have regular interaction with the technical experts from the industry. Your future may be to join maybe tire company
or some of the leading hardware company,
or can even plan to start your own small scale industry. So it is better you have regular interaction with the technical experts of the rubber industry. The Chennai branch of Indian Rubber Institute, we are planning to conduct series of meetings with topics covering various aspects in the rubber industry in the months to come. We are glad the MOD is going to give support about which Dr. Sri Kumar Nayak
will give online the details about the MR support for such meetings. Again, the next meeting we are planning to have
on
auto molded components. We are going to have a lecture meeting. The topic rubber material
requirements for automobiles, both EV vehicles and IC engine vehicles. This is of great interest for all of you. We will be sending the invitation in due course. Of course, I have to extend my warm welcome to MIT students, to the faculty, particularly Dr. Ravichandran, other faculty members, and also the important industry representatives, both in person and online. And I hope you will derive the maximum benefit in today's lecture. Thank you very much.
Thank you, sir. Thank you, sir, for your valuable words. Now, our Dr. K.R. Ravichandran, sir, going to give an introduction talk about our chief guest.
Very good evening to all the IRI members, participants, or online, and my students. Okay. So to say about few words about MIT, especially to the participants from the industry, to online and offline. MIT was started with that in 1980. Recently celebrated the 75th Planet Together. So we had a 3 days event where we made all the global industry and the governments and had a very and the Department of Reference and Technology was started in the 1988, almost about 35 years. And when we start as a division of rubber technology, way back in 1988, for that, as you go for the great Starbucks after Martin, then again, and a few more checker jobs. A lot of industrial people really want to start MIT at a better point. So that is the interest and the purpose to start at MIT. And from the day onwards, we get constant support from the industry people from CHENNAI, especially from very bad and dark environment. So CHENNAI is almost able to sit frequently and give lectures and give support to the students. And whenever we need some training or some project or some raw materials, we immediately approach them. They do IRI, they immediately help us to get the things done. So that's how the department has gone in support of all the industry, other industries, IRI. And today, I'm so happy. I can see the great Starbucks. I have seen, yes, I used to give a lot of lectures at MIT, the whole building. And today, at this age of 85, both are here. And I should really give a hand. And when I reach to the students, still even at the age, he wants to do something to the academic, especially to the students, and see that the growth of the industry should be done certain part of the community. And our boys also get a good job, put over different industries, and almost all the industries, both that and non that, occupying a physical position. So happy, and even though the students are going for training, whenever we approach it, we will support. for this tour. I'm so happy to welcome all, especially Janagan was so keen. As I said, he almost every month he visits once or twice, and almost every week we talk about the industry and about the department, what to be done and what are the facilities can be done. So such an interaction will be taking place, and I'm so happy to both of you are here at this MIT campus. So at the junction, I should also thank Martin. When I asked for books with regard to data technology, they immediately gave a copy to us, and kept in library. It will be more. It's a very rare connection. I think those should really see that he lives and should read, and still is going to support also. I think he's told me, and we're also the process of getting more traction right? And I thank the Telangana especially for organizing great lecture at the Medi campus. Will be and we are ready to support also with the extent. So as a token of love and commitment, I request the young one with all to the Telangana sir. Now, I'd like to honor to Dr. R.K. Martin for his great support to the campus. So, thank you very much, sir. And especially students should witness their when they are in the young 30s and 40s and now how much energetic they are doing supporting our department. That's how we are here. We are here, and this is what we are doing. So, series of lectures are planned to be here to be held here. So it's a good chance and for you to interact and more industry knowledge you will get. So that's how we will also get benefited. So that's why we really connect more into better work and also some close friend TBI exec from Apollo, Jayaraj, right? He is the man, he is almost come and take lectures whenever we call. And almost when we start, we don't have a lab. We don't have that. The first three batches, we just go to the VD scale, and that's how we do the projects and the experiments, practical classes. That's how we slowly we expanded. And now we are in a full facility there. So in this few words, I welcome all the participants in the industry and from the online for joining and also the students numbers and to hear the great lecture to be delivered by a student. Thank you very much. Special reference to be given by Dr. A. Srikumaran Nair, DQ R&D, MRO. He'll be joining online to deliver his.
I hope I am audible. Yeah. Good evening, ladies and gentlemen, and thank you, Mr. Janakar, and the IRI Chennai team for this opportunity to have a special address for you. Glad to know that Dr. Mathani is giving a lecture on technological innovations with the latex material. Sorry that I couldn't attend to the meeting in person, but I'll be joining in future meetings related to the technical lectures. I congratulate IRI Chennai for organizing such innovative programs. And I also understand that IRI Chennai has future plans to have a series of such technical meetings. I'm also glad to inform you that MRF has agreed to sponsor such technical meetings in the near future. Enjoy the technical meetings today and enrich your knowledge and understanding on latex and latex-related materials and the technological know-how as of today. I shall be joining you in future meetings as and when they happen in the upcoming months. And thank you very much and enjoy the technical lecture.
Yes. Yeah. I think it's a great opportunity for all of us. I think they are the first generations of the rubber technologies in the region, which has grown this industry so much. And we are the second generations, and we are the third coming generation. And you will not understand the value of these lectures now. Probably in future you will realize that in other parts of the world, these kind of lectures will be costing so much to get such kind of lectures. And I think it's a great opportunity for you to learn and for us also. That's what we are all coming here. And we need to be a continuous learner. So please enjoy the great lectures, and I'm sure that we will have other moments. And especially the latex experts, I know only few people. Even I don't know much people. Latex is also a very niche area. Unlike the tire, it's popular, but latex is a niche area. In that expertise is very few in the world. That's why Dr. Martin was traveling across the world. Since because of the age only we are able to get him in Chennai. So thank you so much. And General Sir at this age also is motivated to give whatever knowledge we have to share with all the people. Thank you for organizing this meeting. And thank you, IRI, and thank you, Dr. Martin. And in the late evening, you are also participating. Enjoy the class, enjoy the learning.
Thank you so much, sir. So, to introduce our distinguished speaker for the evening, I invite Dr. K. Ilangon, sir, from the Department of Rubber and Plastic Technology.
Good evening, here, respected speaker, Dr. Martin sir, respected IRI teachers, Mr. Jalaga sir, Mr. Sandanam, and respected delegates from various industries, our own colleagues and students, State Movement and Salim, and our students, in fact, some of the MTech students also attending. I welcome all of you and current students and those who are joined in the online also. Welcome all of you for this wonderful lecture. It is a perspective of sustainable data industry, technology, application, and opportunities for innovation. Dr. Ranjit K. Mathan sir, so he is holding a PhD degree from UK, and he is a rubber industry veteran with over 50 years of experience in the Indian and the international rubber industry. A fellow of Royal Chartered Institute of Materials, Minerals and Mining in UK, and the Plastics and Rubber Institute UK. He is also a fellow of National College of Rubber Technology, London.
Since 1975, Dr. Martin has been providing comprehensive technology consultancy and knowledge training across the rubber value chain from plantations to finished products. Dr. Martin joined the Institution of the Rubber Industry UK in 1962 and was a founding member of IRI India in 1988 when it became independent of IOM. Between 1974 and 1994, Dr. Martin served as technology advisor to the Malaysian Rubber Research and Development Board and the Malaysian Rubber Development Corporation. He also held the positions of advisor to Rivatex Malaysia Board 2000 to 2014 and managing director of KA Rivatex India Private Limited 2004 to 2014. He established Polymer Consultancy Services Private Limited in 1974, which has undertaken consultancy assignments for several international funding institutions as well as corporations. From 2014 to 2022, Dr. Martin, as Director of R&D at Five-Star Corporation, Atlanta, USA, led R&D and commercialization efforts for deprotonized natural rubber and latex. He pioneered the large-scale manufacture of several specialty natural rubber products, including ultra-low protein, high-purity rubber, as well as innovative variants such as ammonia-free latex, nitrosamine-free PV latex, and MC latex. Some of these are available both in latex and solid. Dr. Martin is a honorary life member of ARI Managing Committee and served as President of the Indian Rubber Manufacturers Research Association from 2019 to 2020. For his significant contributions to the Indian rubber industry, Dr. Martin received the KM Philip Gold Medal Award in 2008 and the prestigious Hancock Medal from the Institute of Materials UK in 2014. In 2021, he received the Distinguished Service Award of the International Standards Organization, Geneva, for the 15 years of service in the Standards Development Technical Committee. From 2008 to 2024, Dr. Martin served as the Director of the Citadel Institute of Health Research and Laboratory Center in Calgary, Tamil Nadu, which has 3 campuses and also operates a specialized microcellular footwear manufacturing unit for the physically challenged, established with the support of MR Limited. Dr. Martin, an avid reader of historical literature and fiction. Also, he enjoyed playing golf regularly. With this introduction, I welcome Dr. Ranjit K. Martin sir for the lecture. Thank you.
Second shot from the immune system. It's going to sit this and go to I need to. Okay, this can be there.
Yes.
And
Slide changes.
no.
Slide.
1P2. Return.
It's a column make particles.
Yeah.
Fix button.
Full screen mode.
Yes. So just changing the slide, you can. This arrow, sir. Changing.
Here, so okay, here I can.
Yes.
Up and down.
One. Right six. You can use this. This is forward, backward.
This is back.
Yes, sir. This is forward. Yes.
Can you hear me?
Yes, sir.
Okay. At the outset, let me thank the Department of Rubber and Plastic Technology, Head of Department, Professor Dr. Jaykumari, Emeritus Professor Ravichandran, Dr. Elangovan, and students for extending this and organizing this lecture here this evening. Okay. My congratulations to Mr. Janaka, Chairman, IRI Chennai, and to his team, Mr. Sudhakar, who's not here, and Mr. Ganesh, for this IRI MIT interaction initiative, which I'm sure will be a success, and for MRF for its sponsorship of future interactions. Many of you may not know that the late Mr. K.M. Aman Maple, Chairman and founder of MRF Limited, was also the founding member, Chairman of IRI Chennai, then started as PRI Chennai in 1970. MRF has always been a strong supporter of IRI and sponsored the IRI's first national seminar in 1988. This year, IRI was awarded the prestigious K.M. Philip Gold Medal for its role in training nearly 4,000 rubber technologists since its inception. Many of them hold senior positions in industry and, in fact, have been the backbone of the industry, both here and abroad. All the more remarkable because the training was done purely voluntarily by senior IRI members and university lecturers at the 8 branches of the IRI. It has been my privilege to have been associated with the rubber industry for 55 years, of which nearly 50 years has been exclusively in the field of natural rubber. I was actually, in fact, from 1970 to 1969 to 1975, I was at MRF Limited, and then Tan Sri Dr. Shekhar, chairman of the Malaysian Rubber Research and Development Board in 1975, asked me to join the Malaysian Rubber Research and Development Board as a technology advisor, because at that time, natural rubber was under severe threat from synthetic rubber. The ratio of natural to synthetic rubber had dropped from 75% natural rubber to 34% natural rubber. So they set up an international team to modernize and promote natural rubber. And today, it is 48% natural rubber and 52% synthetic rubber. So we are on par. So that has been, since 1990, my emphasis has been working with the latex industry, both natural and synthetic, where the liquid latex technology embodies colloidal chemistry with materials and behavior that is quite unlike conventional dry rubber technology. It's a whole different universe of when you move from dry rubber technology to latex technology. I have also been privileged to be associated with the PRI and IRI Chennai since its branch formation in 1970. In today's lecture, I have tried to portray a broad review or overview of the latex industry and the processes, products, and technology employed. Of course, because the subject is quite large, I had to edit it and just give you a sort of an overall perspective. And you can always, I have about 8 2-hour videos or presentations which go deeper into each aspect of these. I hope this presentation will highlight the unrealized potential of latex science. I am optimistic of the use of latex to create new products and applications. While you may not know this, latex products have the highest value addition per kg of actual rubber used because generally its products are 90% plus rubber content in the final product. So with that, I would like to move on to my presentation, and I hope you will bear with me if it's not up to the mark. So this is the format for today: introduction, an overall perspective, latex industry, upstream, midstream, downstream, innovations and opportunities. So in the introduction, natural rubber and natural rubber latex are important segments of the rubber industry. Globally today, natural rubber comprises 48% and synthetic rubber 52% of the rubber sector. Natural rubber constitutes 11% of the rubber sector in both production and consumption. Similarly, synthetic latexes also contribute about 10% of the synthetic rubber industry and is used in a wide variety of applications. So here I have tried to give you the overview of the three sectors of the latex industry. We have the upstream sector. We have natural rubber in latex form, unprocessed field preserved latex, liquid field latex, centrifuge latex, low protein latex, low ammonia latex, nitrosamine free latex, and synthetic rubbers in latex form. In the midstream, we have natural rubber as pre-vulcanized latex, graph rubbers, epoxidized rubber, latex made in dry forms, oil extended, and master batches. Synthetic elastomers have niche market applications. Downstream, there are a wide variety of products that illustrate the breadth of applicability of latex materials. It is used to make delicate medical devices such as high-performance aqueous adhesives, surgeon's gloves, cardiac catheters, sheetings, and tubings, as well as simpler products such as toys, balloons, thread, rubber band. So we will cover each sector very briefly. So the relative share of the market, you will see here that on the right-hand side, natural rubber 48%. There are three segments. 8% is the RSS, the visual grades. 33% is the block rubber ISNR grades, and 5.8% is the natural rubber latex grade. And then you've got the breakup of the various synthetic rubbers here. Emulsion SBR, solution SBR, BR, isoprene rubber, EPDM, isoprene butyl rubber, nitrile rubber, chloroprene rubber, and SPS blocks. And on the right-hand side, I've shown you the share of natural and synthetic. Natural rubber latex is 1.51 million tons per year. RSS grades 2.6 million tons. TSR grades 11.2 million tons. So that the total natural rubber of all grades is 15.2 million tons per annum that is consumed. And the total natural and synthetic rubber is 31.5 million tons globally. So coming to latex production, we have got today 15 lakh metric tons of latex out of a total of 145 lakhs of natural rubber. So the latex share is 10.3%. And the growth rate has been 3% for latex and 1% for natural rubber. This period is low because of the COVID effect. But it's picking up, and I expect we'll be back to 6 to 8% growth in the 2025 to 2030. In terms of consumption also, you can see today that it is 15 lakh metric tons of latex and 152 lakhs of natural rubber total. Latex share being 9.7% in the latex of the total rubber industry. There was a drop in the latex consumption. Again, it was due to the impact of COVID and the collapse of the plug market post-COVID. So globally, if you look at natural rubber, you will see the gradations in color. You've got natural rubber at 48.3, synthetic rubber, the spread across the world, synthetic rubber 16.3, and natural and synthetic at 32 million metric tons per year. In fact, I had the breakup of the consumption by country is given there, and you see that natural rubber is about 7.2 tons. Can I minimize this here? It's blocking my, no, here. Can this be reduced? Yeah, so you can see that China is 37%, EU 10%, USA 9%, India at 7.5% in the ranking. Not moving. Okay. So here you will see the consumption in 2024. India had 105,000 metric tons of consumption. And that was 7.1% of the total global consumption of 1.549 million tons. And I've given the breakup of the various countries. And you'll see from the table at the bottom that Asia's total consumption is nearly 1.3 million metric tons per annum out of 1.5 million total latex global consumption. So Asia is 86% of the total latex consumed to make products is in Asia, in the countries of Asia that I have listed here. And from there, if you look at it, these are all products made in Asia, but sold worldwide. Malaysia and the glove market is of the order of 300 billion gloves per year. 300 billion, that is 30,000 crore gloves are produced every year and exported from Asia around the world. Like that, most of the rubber products are made in Asia, serve the world. So this is an opportunity for those of you to look at the latex market as a growing market and a potential to work in that industry. I've included, I'm not covering synthetic rubber latexes there now, but here you've got 9 of the major synthetic rubber latexes. The 2 in blue, carboxylate, the emulsion SPR, and nitrile latexes are the most popular. Carboxylated nitrile latexes is used now very much in gloves. It's a big use in gloves, and it has displaced from natural rubber gloves from 100% to down to about 50%. So now nitrile and natural rubber latex are almost equal in the glove sector, but the glove sector itself has grown so much that there's been no drop in consumption of natural rubber. In fact, more natural rubber is used in gloves today than was used 10, 15 years ago. Here are some pictures of, on the first row, you've got some old trees from Malaysia. In the second row, you see the traditional cup for is it cursor is there? Yeah, traditional. And here you see, after we've done the tapping on the lower panels, we now tap the top panels so that we get a total of about 30 years of tapping from one tree. And once a lower panel is fully tapped and there's no yield, we move to the higher panel and tap, and we can even do atrial stimulation at the top so that we get good yields. And this is how they make the coagulum. And these are the bottom row, you've got some of the early macerator, baling press, and preparation of coagulum seed. So from the field to the process factory, you've got tapping and collection of latex, preservation for dry rubber grade, preservation for centrifuge latex grade, bulking and standardization once it reaches the factory, and then pre-processing operations such as desludging and testing. Now this shows you the spectrum. You've got the rubber seed at the left, and those plastic things are what we call root trainers. We put coir pith inside and we put the seed, and then in these containers, the second picture is of a taproot. And then once the plant bush has grown that, we actually cut off, we graft the actual clone, which is going to yield onto this first one, and we cut off the original plant on the left side. This the original tree. We cut this off and allow the clone to grow. And you can see this is an automatic machine for filling uh, because can you imagine that in one acre there are 700 trees to be planted. So if we want to make root trainers, we have to do 700 cups per acre. So if you're doing 100 acres, you've got to do 700,000 things. So we have automatic filling machines, and we then bring it into the stands, allow it to grow, and then we try to also increase the foliage of the tree through special bud grafting, so that the absorption of CO2 is increased. I'll show you later how much absorption of CO2 is done by the rubber tree, and we are increasing the foliage to increase the absorption of carbon dioxide. And we have achieved yields of up to 3,500 kilograms in the plantation that we started about in Guatemala about the early about 20 years, 15 years ago, and their yields are getting up to close to 3,000 tons, whereas we are only getting 1,600 kgs in India at the moment. So there is plenty of scope to increase the yield per hectare and get more rubber from the existing plantation. So there is a real scope to upgrade the plantation's productivity and go at least from 1,600 to 2,000, 2,500 kilograms per hectare. Today, we are importing 500,000 tons of natural rubber every year. That's a shortage. Our downstream industry is growing so fast that the shortage is increasing every year. So again, this is a sequence: seed to root trainer, to hardening of the plant, to budding, then to bud grafting. Then in the nursery, we do plant protection. The nursery for 2 to 3 years where it grows, we need to spray irrigate. Then we transfer to the field. Then we take it in the field and see that the root system and put it in the field for 6 years. In between the 6 years, there's no yield from the tree. But what we do is you grow corn or you grow pineapples or you try and do some supplemental income during that period. So I talk about the whole spectrum of natural rubber, sustainable natural rubber grades. On the left side, you will see the traditional visual grades that have existed: air-dried seeds, RSS grades, brown grapes, latex grades. And on the right side, you've got the modern grades of. That's the grade that we started doing in 1975, introduced the modern grades, which are technically specified. The ones on the left were visually graded. The ones on the right were technically graded. So the user industry found it more acceptable to get the technically specified. And what I've shown you on the far left is the subsidiary grades of rubber that we could get out from the traditional grades. And on the right-hand side, these are the modern modified rubbers that we can get from the block rubber grades by using whatever technology that we have, which we'll talk about later. So here you have the latex sequence from the tree to the factory: tapping, latex flow, collection. The tapper goes to the center, latex is weighed, then it goes into bulking tanks, then it's transferred from the bulking tanks to lorries, containers, and it goes to the factory where it's unloaded into the first tanks there. And So latex from all over the plantations will come every day and be unloaded into these bulk tanks at the factory. This is a bank of 16 centrifuges. There's a factory we set up in Guatemala. They have actually 16. Now we added another 16. And roughly it produces about 16 to 18,000 tons of latex a year. And so one of the important steps in latex is the preservation of latex. We traditionally use ammonia and for high ammonia, TMTD, zinc oxide, and ammonia for low ammonia to prevent bacterial attack and degradation of the latex. The bacterial attack occurs because of proteins and sugar in the rubber serum. Because ammonia is now considered a volatile organic compound, there are other systems that have been developed and put into place. This is the typical centrifuge that we take the field latex. There's a pre-processing, which involves testing of the latex, filtration to remove any coagulum, desludging to remove magnesium. The magnesium in the latex varies according to the season, and it will be low most of the year, but around the defoliation season, the magnesium goes very high because the leaves are not removing it. So we have to remove the magnesium by using diammonium hydrogen phosphate. Then the desludged latex goes to the centrifuge. So the green arrow into the machine in the center. I don't see the. This is no. I want to. Doesn't show. There is a cursor here. I want the cursor here. Cursor is not here. Ah, okay. Okay, so the latex, the field latex comes in to the center, and then the centrifuge is spinning at about 10,000 RPM. So because the density of rubber is 0.92 and water, the serum 1, the heavier goes to the outside. That's a blue color. And the latex comes through the inside. There are a whole lot of discs through which this goes. And the yellow part is the latex coming out, and the output. The input is 35% rubber and 65% serum. The output is 61% rubber and 39% serum. So that's the centrifuging stage, but we still have to mature the latex. We have to stabilize the latex. We have to standardize the latex. And that takes about a month. You have to keep it. What happens during that period? There's hydrolysis of the phospholipids. You get the formation of natural fatty acids that act as natural stabilizers for latex. So the latex stability will, just after centrifuging, the latex stability will be about 200 seconds. But after 3 weeks, the stability will go up to 700 to 800. Naturally, because of the biogeneration of natural higher fatty acid food. Then we test and pack it. And latex preserve can be kept for 2 to 3 years. So these are the main basic specifications for latex. There are 3 basic grades: high ammonia, medium ammonia, and low ammonia. And you can see that there are 10 tests that we have to comply with under the ISO. So these specifications have no resemblance to dry rubber grades. You've got total solid content, dry rubber content, ammonia content, non-rubber solids, volatile fatty acids, which are the acids like acetic acid, propionic acid, butyric acid, the KOH number, which is the total volatile and higher fatty acids, the good and the bad, mechanical stability time, coagulum content in the latex, because it's a liquid, we want to have the minimum coagulum in it, the copper content and the manganese content. So these are the ISO specifications for the basic 3 grades. There are, of course, other grades, and ASTM also has a specification which includes the low protein grades and the cream grades. There are other processes to make latex. So when we come to the specialty grades, we have natural rubber latex, high ammonia and low ammonia. Then you have the ultra low protein. You have the nitrosamine free, where we remove the nitrosamines. We have ammonia free, ultra low protein latex, pre-vulcanized and graft lattices. And in the center, we are creating this FSC bioelastoplastic material, which is the latex of the future. And this includes its FSC certified, organic certified, Forest Stewardship Council of Geneva will certify it as organic. And you have forest management certification, you have certification of conformity, and your carbon neutral certified. So you have a very sustainable material coming out of here. And no synthetic rubber can be as sustainable as this. These are just 2 of the grades, new grades that we have developed and put into the, with some of our people. On the right side, you've got a low nitrosamine latex. We use a special dispersion to extract the nitrosamine out of the latex and replace TMTD, which is one of the preservatives. We've replaced it with a non-nitrosamine producing preservative. And on the left-hand side, we have another system where we don't need ammonia. We have another chemical composition, dispersion, which we add, and then we can have latex without ammonia, so that you don't have the problem of smell of ammonia, volatile organic content in the factory. And from these, we have basically 4 grades you see on the bottom. NF low ammonia, nitrosamine free low ammonia, ultra low ammonia, no ammonia, ultra low protein, high ammonia, and low ammonia. And these are the formulations on the right side. Then we move to the midstream. So we've covered the upstream part of it, which is the latex and the special preserved latex. Here we have the pre-vulcanization grades, low and medium and high modulus, and the innovative specially modified lattices, DPLNR, MG latex, epoxidized latex, custom graft latex, physico-chemically modified lattices. So these are a whole stream of these. These are in various stages. They are all capable of commercial production. They are being produced in commercial quantities in various parts of the world. So if you are working with these materials, we can arrange for you to have some of these materials for your development work as well. So these are the main midstream materials that you can have as a processing technologist to work with and to create products with different properties and different applications. For pre-vulcanization, is a unique factor of latex. I mean, you can give your customer a fully vulcanized product, and all he has to do is dry it and shape it, and he's got the product. Whereas in dry rubber, you've got to add all the powders, you've got to first of all, you break down the natural rubber, you lose its beautiful macroelasticity, and then you are dumping all these powders into it. And we are clean. We put the chemicals by way of a water-based dispersion into we vulcanize it. The latex remains as a 60% solid, but it's fully vulcanized. So you can now process it in your factory as a vulcanized latex product. And you don't have to wait to do everything and then have it vulcanized at the very end. And we have basically 3 processes: the cold fast process, where latex is heated to 60 to 70 for 2 to 3 hours and cooled, and 6 to 8 days of maturation. Here, the latex suffers both chemical and thermal shock. We have the hot fast process where you can heat to 70 to 80 for 4 to 6 hours, remove the excess chemicals, and then you can have it ready within a couple of days. So here also there's chemical shock and thermal shock. In the cold slow process, we stabilize the latex, we add the chemicals, it's at room temperature. They're very fast room temperature curing chemicals, and we keep it to 30 to 45 days. And here there's only chemical shock. There's no thermal shock. And because of that, the latex is much more stable. What happens when we add in the dispersion chemicals into the latex suffers a shock. You can see the mechanical stability go from 400 down to 200. And then slowly over the next few weeks, it go back and it goes up to 700 to 800. So you have to, your best, the process that at Revatex we were using and which we introduced here in KA pre-vulcanized is the cold slow process. But when we are doing 100 tons, that means we are storing 100 tons of product for 30 to 45 days before we can send it out to the customer. That's blocking up a lot of inventory. But there are advantages to that. Then there are other methods of pre-vulcanization, peroxide and radiation. But these are maybe 1% or 2% of the total market. So when we're compounding latex, you have the latex, you add the stabilizers first, stabilize the latex, then you add the vulcanizing dispersion, and then you add the other materials. So that sequence follows of doing the pre-vulcanizing. I've given a little calculation on how we actually calculate the quantity of dispersion. We make the formula in dry rubber on a DRC basis, but then we prepare the dispersions at 50% aqueous, and we have to add it into the latex. These are the parameters I've given. When we take latex for pre-vulcanization, we have to make sure that it will not coagulate when we add all these chemicals and heat it, thermal shock, chemical shock. And these are the specifications we give the supplier of the latex to give us. And the MST gives us the ability, the stability, mechanical, physical stability of the latex. And what you see on the right-hand side, zinc oxide viscosity, zinc stability time, zinc heat stability, that's the chemical stability of the latex. So you have the physical, mechanical stability on one side and the chemical stability. So we want the latex to come in at these parameters so that we know that there will be no coagulation and no batches will get spoiled. Now, this is just a list of the various ingredients that we use in pre-vulcanization: surface active agents, vulcanizing agents, accelerators. These are all very fast curing accelerators, but unlike natural rubber, we have no scotch. We can add the fastest of accelerator, but the latex is still scotch free. Then activators, antioxidants, the styrinated phenols, and we want non-staining antioxidant because most latex products are light colored. So we don't want staining antioxidants which are used in dry rubber. We use non-staining antioxidants. And fillers, again, we don't use much fillers in latex. Latex products usually have a very high rubber content, and it is not with fillers and not with process oils, and all these are not necessary because the processing does not require that. So here you see on the left-hand side, the individual rubber particle, which has a protein sheet, a phospholipid layer, and inside the particle, the rubber particles. So the rubber particles are protected by this protein sheet. And then you can see in the middle, when we have pre-vulcanized the latex, the red, we cross-link the latex inside the particle. We allow the dispersion to enter into the particle by suitable chemical modifications of the surface, and it enters the particle and it vulcanizes the particle. That's the intra-vulcanization within the particle. But there's also from the serum, the sulfur will also cross-link between particles. So you've got the interparticle vulcanization also. And so you have this, and then that, when we coalesce and gel it, that integrates to form the droplets will all coalesce together and it will form a film. So you can make very thin films of 0.02, 0.023, very thin films to very thick films. So this is the protocol we follow for revulcanization, selection, stabilization, addition of dispersion, stirring for 24 hours, stirring for 12 hours, for 30 minutes, maturation for 25 to 30 days, protocol testing of key reaction progress and stability parameters, testing and standardization. So these are some of the comparisons between, we have pre-vulcanized and you can have post-vulcanized. Post-vulcanized is where the factory is doing its own vulcanization. Pre-vulcanization is usually done by pre-vulcanization latex suppliers who supply latex product manufacturers. And so these are the advantages of cold pre-vulcanized latex versus conventional in-house post-cure, which many companies prefer to keep control of their curing. Maybe they have got some special formulations or think they have some special formulation, so they don't want to share it with you. But we can give the cold pre-vulcanized latex at the same formulations as they want. So I've just done a comparison between, you will see on the right-hand side is all the steps that you are required when you do conventional post-vulcanization in a latex products factory. And it's a much more simple process on the left side where you have pre-vulcanized latex and you just bring it in, dilute it, and then feed it into your dipping line and dry it in the oven and get your product. So there are, as I said, there are three primary and secondary grades here, low modulus, which gives you these grades. It has a toluene spell index of 100 to 110. That's a measure of the cure of vulcanization that has taken place. And medium, and you see the products that are produced from there. Medium modulus, you'll see that the cure has gone a little further. It's 85 to 100. And in high modulus, for products like condoms, it is at 72 to 85. There are other stiff products, such as CTO3, where we use a little bit of MG graft in the product. And so these are the basic range of the products. There are many subgroups as this. This shows you just our product brochure, which has 34 products of pre-vulcanized latex and special latex, and 9 properties are specified, and there are given some 14 applications to which the basic applications where this goes. Now we move to the downstream. So that takes care where the latex is midstream comes into the downstream area. So these are some of the latex application products. You've got condoms, gloves, cast toys, toy balloons, elastic thread, continuous tubing, Foley catheters, latex foam, spread and coated products, adhesives, fashion wear, heavy duty latex products. So this just shows the consumption in India in the last 5 years. And you can see that there's been a healthy growth in Indian consumption. And I expect that this will continue through the next 10 years. And we'll probably go from the present level of about 100,000 tons to 200,000 tons. So you can imagine the opportunities it creates for new products, for new people to work in the industry. And here I've given the consumption of various countries. Malaysia was the leading consumer of latex for gloves, but it's been overtaken by China. Malaysia focused too much on gloves. So after the COVID, there was a collapse in the glove market for some time because of overproduction. So they lost out, but now slowly things are picking up again. And so the breakup shows that this consumption of 1.3 million tons as of 2024. And this I've segmentized the various products that go there. Medical gloves, diagnostic gloves, surgical gloves, special gloves, they are 52, 53%, other gloves, 6%, condoms, 5%, catheters, 4%, latex thread, 10%, balloons and teeth, 9%, carpet backing and foam, 4%, 2.1% other. Foam is making a big comeback. Previously, it had been sidelined by synthetic latex, but because of the sustainability aspect, many people have switched back to natural rubber latex. And many products, latex products, are now have increasing content, if not wholly, of natural rubber foam. Even in Europe, we found that we started supplying previously 100% synthetic latex people into moving into natural rubber latex foam. There's a general manufacturing pattern for latex dip products, and I've tried to show you that sequentially. The mixed design, dispersions are added, and the latex stabilized, the dispersions are prepared, added to the latex for compounding, pre-vulcanization, or go straight to the manufacturing line, post-vulcanization, drying, finishing, QA, final inspection, packaging, dispatch, and you may have some special treatment done at it, chlorination to give you a high friction-free surface, acrylic coating to protect against protein interference, sterilization. A lot of gloves, catheters, medical devices are all sterilized. So we use either gamma or we use or ethylene oxide for sterilization. So I'm just showing you what are the colloidal properties of the latex that we use for making balloons and toys. So we have colloidal properties, and these are the physical properties that we will get out of the product. These are tailor-made for the balloon. Here's the for the condom. These are the colloidal properties, and these are the physical properties. Balloons are dipped and coagulated with a coagulant. Condoms are not, don't use a coagulant. They are dipped and double dipped and dried, and because the films are very thin. So you don't coagulation dipping will make thicker films. So these are some of the colors that we have. The basic balloon colors: red, yellow, blue, orange, green, purple, pink. So we can supply pre-vulcanized latex to you in these colors. So you don't have to do your own pigmentation. And these are pigment colors also for different applications. And you can see the different types of balloons. The metallic colors are very popular now. Balloon is a big industry event for event management in events. So just apart from being balloons being used for toys, but for event management, there are huge quantities of balloon, which probably constitutes about 60 to 70% of the market. This is a typical sequence you see for the condom process. You can see former cleaning, former drying, dipping, drying, dipping, double dipping, drying, bead ring formation, drying, curing, leaching, stripping. And in condoms, we use glass formers, whereas in gloves, we use ceramic or porcelain. And now lately, people have been experimenting with plastic formers as well. And these are the properties that you are aiming for in the condom. It has just go to 9 electronic testing. You need 100% safety, and shelf life simulation requires that you test in real life for 3 to 5 years before your product can be released into the market. Coming to gloves, which is a big segment, there are 10 varieties, basic varieties of gloves. And you can see that exams, surgeons, orthopedic, microsurgery, gynecology, postmortem, electrical, clean room, veterinarian, and industrial gloves. So this shows you this typical production cycle and a production line. It's pretty much typical, and there are videos of this are available online. So then we've just put together the benefits of using natural gloves, benefits of using nitrile gloves, the benefits of using polychloroprene gloves, and the benefits of using synthetic rubber. So each has found its own niche and space. The two largest are, of course, major segments are natural gloves, natural rubber gloves, and nitrile gloves. And the others go more for niche applications in the market. So this is the typical specifications of the PB latex that is used for making gloves. Colloidal properties and physical properties. So you have both the unaged and the aged thing. And then for gloves, you have what are the properties that you're looking for. Thickness, visual dimensions, tensile strength. These are all covered under various standards under the ISO. Note freedom from holes is 100%. These are electrical gloves. We have electrical gloves that can withstand various maximum voltages. You can see the proof. To get a max use voltage of 36,000 to 54,000 DC or 36,000 AC, the proof test voltage it has to pass is 40,000 AC for AC current and 70,000 for DC current. So these are all they come in various colors. They're made from natural rubber and they're quite thick. And then we were able to introduce ultra low protein rubber, and we found that the voltage ability went up by almost 20-25%. So many of the electrical glove manufacturers use protein-free glove because the protein will allow, otherwise presence of protein allows for little migration of moisture into the glove over time. As the glove gets older, there will be more moisture into the glove. So the ultra-low protein allows for the glove to be protein-free and no ingress of moisture during the service life of the glove. These are something called dental dams that your dentist uses inside the mouth and doing various procedures. Most dentists will have these, and these are very fine rubber sheets. This is another big one, which is the elastic thread and tape. You've got the elastic thread, which are individual threads. We extrude the individual thread through very fine capillary tubes. We make the thread, we dry the thread, we vulcanize the thread, and then we bring it together and we make tapes of it. These are easily spreadable tapes. So these are required by the hosiery industry. Then the tapes on the right-hand side, you see they have been fabric has been or various tapes have been made using cloth. There's one on this. This is just a toy, and then you see the various types of thread. So this is a typical. We have standard latex, and we have heat detergent resistant latex because latex is used in underwear, etc. It goes repeated washing cycles, exposed to detergents, and in abroad they use dryers. They use hot dryers, so they go through many cycles of detergent and drying. So we have heat-resistant latex thread and normal latex thread. The normal latex thread will go for various types of applications, including socks and things like that. And this shows you the main segments of our latex factory, Thitex in Malaysia, where we have introduced them. They use our special formulations, blending natural latex with PV latex and making the thread. This is tubing. Latex can come in tubing. Now there are some specialized manufacturers who can make latex tubing that are up to half a kilometer in length, continuous tubing. They use a wire mold, and it, as you can see, it goes below this. There is a latex tank, and the wire goes multiple times through this latex bath and builds up the thickness, and then it goes into a drying oven where it is dried, and then finally there's a mechanism for yanking out the cord, the wire from the center of it. And you can get these not only in the normal natural black and brown colors, you can have, as you can see, you can get them in various colors. They go for applications including scuba diving and various other medical applications. So these are the products that come out of that. And sheetings, we can make sheetings of any length and thickness. So there's latex calendar sheeting where we cast the latex and then we fine tune it through a calendar. We can make anti-static sheetings, food grade sheetings, heat resistant grade sheetings, medical grades, natural rubber latex, and synthetic latex sheeting. So these are various applications. And you can see even in fashion wear, this dress is made out of this material that you see here. There's a company called 4D in UK and others in Germany and in US who make this fashion wear made purely out of natural sheeting. So this is medical and fashion and mode sheeting. Now this shows you heavy duty latex products. You can see they are much thicker and they can be used for various types of lining, acoustic lining, lining of pipelines. There's a company in Malaysia called Linetex, which does quarry lining. And a quarry is a very abrasive material. The abrasive wear is much more than, much harsher than what a tire abrades, but it can withstand that. So it's made, again, it's a process of casting of the latex, go through a continuous microwave curing. So as you build up the layers, the microwave cures it, and then you can have it in black, you can have it in various colors as specified by the user. And then they can be used for lining of pipes and valves and things like that. So this is the more, and these are many other industrial applications that can be explored, replacing natural rubber, dry rubber products. This is a very important product, catheters. Every time you go into a hospital for a procedure, they catheterize you so that you don't have to pass urine by yourself. And you can see that it consists of a basic tube with a balloon, and this is inserted in, and the balloon is blown up using the funnel on the left, and the urine drains through the urine drainage port is there, and the balloon port where we inject water and inflate the balloons once the catheter is inside the patient. And you can get them in various sizes. On the left, you've got a pediatric catheter with children. And then you've got, for various sizes, men and women, you've got various types of catheters. And there are other types of catheters that are used in the industry. These all are intra-body use. There's even a balloon that goes for certain heart procedures. It's inserted along with the wire into the heart, and the balloon. Edward Life Sciences, a company in the US, makes those with a deproteinized latex. So you've got all these different products. Here I've just shown you the production sequence for home manufacturing. For manufacture, there are two basic processes. One is called the Dunda process. The other is called the Talladega process. This is the Dunda process. So you see on the right-hand side, that's the machine for making it in a batch way. That means we form the latex in a batch and we pour it into the mold, and it then goes through the whole cycle of vulcanization and stripping, cooling, drying, washing. And or we can do continuous, we do continuous feeding, so that we have a continuous feeding machine, so that as the molds are coming, it's continuously feed. So that's where we have high volume production. We use the continuous feeding machine. In this process, sodium silicofluoride, once we have put the latex in the mold, we have to gel it and make it solid. So we add, in the final stage, we add sodium silicofluoride, which breaks up into sodium, silica, and fluoride, and it quietly gels the latex. So you get a firm gel inside the mold. So that's a Dunlop process. The Talalay process is completely different. We foam the latex, we put it into the mold, we close the mold, we freeze it. We freeze the latex in the mold, and then we pass carbon dioxide gas through it. The acid in the gas gels the latex, and then later on we warm it and we continue the process of drying it. We are feeding this in at 55% solids and 45% water. So finally, after we've extracted it, we have to remove the water. And we were using conventional dryers to remove this, but now we are using things like microwave and radio frequency dryers. So this is a sequence you can see a factory that is making latex foam. This is one we set up in Guatemala. And you can see here in the bottom, you see the red, those are FRP mold, fiber reinforced plastic molds. We pour the latex into that, and it's just going into the vulcanizer. That's a radio frequency vulcanizer. So we cannot use any metal, so we use a plastic. We fill the plastic mold with these are pillows, and it goes into the vulcanizer. On the left-hand side, the black molds are made out of polycarbonate. We first started using polycarbonate, but found that their life, there was, because of the radio frequency, there was cracking after, the life was not enough, but FRP are now working very well. After we make the latex pillows, we have to keep it and mature it for about 14 days before it's ready to go out into the market. These are some big mold making of huge mattresses. On the right-hand side, on the left-hand side, you've got a 8 feet by 6 feet mattress being made. It's just come out of the vulcanizer, and they are preparing to strip it. And on the right-hand side, you've got a mattress that is just come out of the dryer. Whereas previously we needed about 4 to 6 hours of drying. Now with the RF, we can dry it in the matter of 15 to 20 minutes. So we are much more efficient here. Then we have slow recovery foam that we have introduced using a DPNR ENR combination. So normally latex foam, when you press it and leave, it fully recovers instantly. But some of the PUs, when you press it, it recovers slowly. So we have now been able to simulate this with natural rubber foam using a combination, because ENR has high damping properties. So it damps the recovery process. So you can, and the DPNR also helps in that process. So this combination gives you a very sustainable, protein-free, sustainable latex. Met balloons are made both by the dipping process as well as by a rotational casting process. These balloons can range from, say, 3 to 4 feet up to 12 to 16 feet in diameter, depending upon what altitude you want to send it up to. At the bottom of each balloon, you've got a radio sound which sends the typical frequencies data back to the meteorological office. So in India, we have one met balloon manufacturer in Pune. They are now making all the full range of the balloon. But they are made both from natural rubber and polychloroprene rubber, because at the higher altitudes, the ozone levels are higher. The natural rubber balloons used to pop more frequently. So now we are trying to see how we can. The height level of a polychloroprene is much more than it can go to more higher kilometers than a natural rubber balloon. So these are the changes, behavioral changes we can introduce into the latex through various processes. Deproteinization, preparation, removal of ultra-low gel, so we have low gel, epoxidation of deproteinized latex, depolymerized, so it becomes an alternative to a plasticizer, natural plasticizer for dry rubber. You using depolymerized latex to a certain molecular weight and viscosity. Then you have halogenation, hydrogenation, and cyclization. You have custom grafted latex from low purity latex and custom compounded DPNR and ENR latex. There are three processes of hydrogenation: physical chemistry, electrolysis with water, inorganic, metal and acid, organic process, proton dominance. So these are the types we use for hydrogenation of latex. Now, the interesting thing is that the EPDM rubber is a combination of ethylene and propylene. Now, if you look at polyisoprene, if you look at the isoprene unit, it's a combination of ethylene and propylene. So when you hydrogenate and remove the unsaturation, you're getting a natural EPDM rubber. So you can see that in this table, when you get up to 94% of hydrogenation, your temperature, decomposition temperature is up in the range of 360 to 458, as against normal rubber, the decomposition is 250 to 370. So here, an EPDM, as you can see, is 470. So we are coming up with an alternative to EPDM. So we are challenging that theory. And but one thing is, you cannot do normal hydrogen gassing. That doesn't work. You have to have in situ gassing. You generate the hydrogen in the latex. It reacts in situ. So that requires special treatment of the latex to keep it stable during the process. So I'm just now closing up with the prospects in the industry. You'll all want to know, with overall, with production and consumption growing at 6 to 8%, the consumption will go up to 200,000 metric tons, and then that requires an increase in the latex industry workforce in the coming years. And why not produce more trained latex technologists? Global growth also is at 4%, and it will go from 14 lakh tons to 20 lakh tons by 2030. Thailand, the largest producer, has a burgeoning latex product industry, and I know of several Indians who are working in that industry. Thailand is the largest producer of natural rubber, 5 million tons, and about 100,000 tons of latex. So they are now, instead of exporting it, they're converting it to product. That means they need more techno factories, they need more technologies, and that is happening. And then there are specific opportunities for latex chemists, plant processing technologies, quality assurance, R&D, and technical service support. Startups at cooperative production and marketing venture option with MSME ministry support, entrepreneurial opportunities with modest capital requirements. Already we see Indian latex technologies in Thailand, Malaysia, Mexico, USA, Canada, and Europe. I've interacted with several of them, and they're all doing a great job abroad. Maybe some of you will serve also around there. Now, these are the process and product development opportunities that I've just listed out. Upstream, what is their possibilities in basic latex? Midstream, in the preparation of intermediates, what is the prospect? Opportunities of new product innovation downstream. Maybe some of your project programs for your project work, we can give you the latex and help you with the modification process, maybe interest industries to adopt this on a scale. So this basically the idea is that natural rubber latex should be able to produce any product that dry rubber can produce, and that should be the goal by 2030. We tested, our partners in Europe tested natural rubber latex, and we got a certification as 100% bio-based carbon with zero fossil carbon. So we are sustainable as hell. So there we have CO2 absorption, 25 million metric tons of CO2 in the previous year, a pair of gloves, 25 grams of CO2 sequestration delivered, 100 billion pairs net carbon sequestration, 250 2.5 million metric tons. So there, rain or shine, we think of latex as a sustainable sunrise industry. Thank you. I'll be happy to answer any questions. You may, as a point of interest, know that MRF started off as a balloon company in 1947. Mr. Baman Maple and his wife started a balloon factory there in Tiruvuttur, and that graduated with his entrepreneurial brilliance to tread rubber and then to tires. So the balloon can be a start of something big. Yes, sir.
Thanks for that. So actually, my point is hydrogenated natural. So we were saying that there is a more of saturation. So now the tire industry must focus on hydrogenated SBM in order to reduce the PPE. So the problem that tire industry facing is curing. Curing.
Yeah.
Curing system. So if a hydrogenation will come, the sulfur curing is not possible. Only peroxide curing. Now this thing will be overcome for tire industries.
There are you talking of 100% hydrogenation? See, here we can control the hydrogenation and drop in unsaturation to any level. We can do 50%, and that means the residual unsaturation is available for cross-linking. You know, you've got natural unsaturation, so whatever level, you may offer 3 grades, 50%, 75%, 90 or 95%, you know. Then you don't need EPDM, you have something like a norbornodiene as a unsaturated, as a cross-link added, the diene monomer for cross-linking. So you don't need that. So your cost of hydrogenation can offset that.
Will be slow curing.
Will be?
Will it be effective curing? Will it be slow curing or what is that?
That's the level of hydrogenation in the curing system that you employ will be there. Because we are making the latex, we can give it to pre-cure. Maybe or with the additives there. So if you want to process it in that way, you can process it that way. So there are all types of, you know, where your double bonds can open up when you're processing it and close in again. Polysulfidic, as we do with some formulations, we can open the cross-link and later on it close. There's a lot of latex chemistry which is not well known, and you know, you would there's a lot of things to be learned and to be tried, and latex is a brilliant platform to work with.
Is it possible to make smellless nail odor latex?
Pardon?
Nail odor, smellless,
Odorless.
odorless.
Yes. Yes. We have made it, and
If we remove protein, like deep protein,
deep protein, you have to remove the other non-rubbers as well. You have to get to virtually.
Which element causing smells and latex?
You know, unfortunately, I'm under an NDA with a leading company which has gone through 2 stages of approval abroad, and we are in the 3rd stage of where it's going to come products for testing in vehicles. So it's going to that stage. The requirements, nil odor, absolutely, especially in closed environments.
Yes.
You know, so you need nil odor, and it can be done.
One more question there. So why in India ENR is not commercially available?
what quantities do you want? Where our associates have just sent about 200 kilos to Calcutta. We can give at various levels of oxidation. Most popular is about 25%, but for many applications, people want 50%. One of the drawbacks, of course, is the methodology for prevention of rapid oxidation. And so that we are now trying to build in at the manufacturing stage itself, so that the oxide rings are stabilized at that level itself, and it will not open like a zipper.
Thank you.
Then we'll try to, whether online any question is there. Yeah. I can just check out. I can tell them if they have any queries, they can go. They can.
For online participants, have any questions? Kindly ask. I repeat, online participants can ask questions.
Good evening, sir. As part of sustainability, recycling of recycled products getting more and more importance. What is the scope of recycling in latex?
Latex products are very easily recycled, much easier than a tire or something like that. Many people are doing gloves, of course, are recycled. I mean, when you talk about 300 billion gloves, at least 300 million goes as waste. You know, there's a regular recycling industry but we did recycling with gloves at Gujarat Reclaim, but we found that the rubber content was too high, so we had to add filler to make it more compatible for the user industry. So the rubber content of whereas with reclaim rubber, you get 50%, I think, you know. Here you're getting 92% of rubber coming out. So it's very high and much higher molecular weight. Your strengths are higher. And that's in fact, the tire industry should try using recycled latex rubber rather than reclaimed rubber.
The challenge is the collection.
Yeah. Collection, yeah, there are. I mean, in India, not so much because we are not a very big producer of gloves. But Malaysia, China, Vietnam, Thailand, all collection is very well organized. Very well.
Thank you. Does anyone have any questions? Kindly ask. Online participant can ask a question. Doctor, can there be any work that today you can reinforcement material used in regarding that? Only synthetic bags are used. Any work must be done either illegal or using natural methods.
For
You take nylon bag.
Oh, you mean for coating, for coating? Yeah, one of the problems earlier on was, the original formulations had natural rubber latex for nylon dipping and nylon dipping. But latex stability in these high-speed dipping machines, because the fabric is running at such high speed, there was the development of coagulum was much higher with natural rubber. The synthetic rubber lattices are extremely stable because they've got a much higher content of soaps, and their particle sizes are smaller. They don't form coagulum that easily. Their mechanical stabilities are of the order of 3,000 as against natural rubber we get 800 or so, 1,000. Now with the ultra low floating, we have started getting mechanical stabilities of 2,000, 2,500. But so basically, I remember at MRF we were getting the original formulations had natural rubber, and then they had to be changed to synthetic rubber latex. So, and today I suppose the growth of fabric coating is not a growing industry, I believe, as people shift to steel and other things. But today, probably the latex industry can give you much better material.
Does anyone have a question? Kindly ask. For online participants, can ask question. Thank you, sir, for the enriching session. Your depth and knowledge and clarity of presentation have given us new perspective and deeper understanding. Thank you so much, sir. To formally conclude today's program, I invite Pran sir to give the vote of thanks.
Good evening to all. Thanks to Dr. Martin. He gave an excellent presentation. And hats off to him at this stage. No, he was really. Thanks to Mr. Janakar, who organized this meeting along with Dr. Ravichandran, Dr. Jaykumari, Dr. Ilakovan, and all. Thank you all. Thanks to MRF for sponsoring, as Mr. Janakar was telling. Today's meeting was sponsored by Polymer Consultancy, Dr. Martha. And we are going to have a series of lectures, maybe 8 or 10 lectures that will be sponsored by MRF. So my request to all of you is please use this opportunity. It will definitely help you in your career. Okay. And last but not least, each one of you on a Saturday, I know you guys must be really getting bored. So in spite of that, you are all over there. All the best to you. Thanks.
Thank you so much, sir. So thank you so much for your patience. So now it's a photo session. So kindly occupy the front podium.
Yes, we'll take this way.
Yeah.
Thank you very much for He wants to drive.